I'll tell you a story. A story of man's ambition to win, to be the best. It's a story that started not far from here, more than 50 years ago, by a man named Bruce McLaren. The aim was simple. The challenge was not. To take on the giants of the sport and to beat them again and again. A race team was born and a legacy written. Written in actions and achievements, not words. And the achievements grew. Champions were made. Records were broken. New chapters were added to this great story, each better than the last. But as the achievements grew, so too did the ambition.
The most successful debut by any manufacturer in the history of Le Mans.
The name McLaren came to stand for so much more than racing cars.
This could be the shape.
It became a byword for innovation, for setting new standards in everything it did. The seed that was planted many years earlier had now grown beyond its founder's wildest dreams. As McLaren's reputation spread, its business grew ever stronger. And so a new dream took shape. A world-class home for a world-class company. An environmentally sensitive architectural icon, shaped by the DNA of the brand. A showcase for achievement, a center for excellence, a quiet, beautiful, and exclusive environment, a cradle of innovation. A technology center where people come together from around the world to share in the spirit of progress, to advance the outer limits of possibility. McLaren. It's a simple story, and you are in it.
Okay, good morning everybody. My name's Simon Roberts. I'm the Chief Operating Officer for McLaren Racing. This morning I'm going to give a very quick insight into our latest thinking in 3D printing. McLaren as a brand, as you saw there, is actually more than just a Formula One racing team. There's three main companies in the group. Racing is around 700 people these days. In McLaren Automotives, about 3,500 people building the supercars, and in McLaren Applied Technologies, around 150 people who are in industries as diverse as medical, transport, and also supporting motorsport. So it's a pretty exciting place to be. The factory you saw there is where I work, and it's pretty cool every morning when you drive in and walk those corridors. So the reason I'm here today is to talk about what we're doing with Stratasys. So Stratasys is a technical partner of ours, and from a Formula One point of view, what we try and do with a technical partner is work very deep and very close. So we bought our first Stratasys machine in September 2016, and the reason we bought it was some of our suppliers were using that technology, and it was just cheaper for us to buy the same machine and then supply them the tooling rather than make it. So a pretty straightforward kind of business case. But very quickly in working with Stratasys, we realised there was more we could do. And in December 2016, we signed a 4-year agreement with them, a technology partnership. And they kind of got what we did and we got what they did, because by February we had 8 machines installed in the factory and running in full production, which is pretty impressive. And those machines are still running today. And since then we've added one more machine which we actually fly around the world and take around the world in our trucks to all the races. The key thing we're trying to do with them and that they want to do with us is push this technology forward. So we've been using rapid prototyping techniques now for 15 to 20 years, but we kind of feel like we're on the edge of a breakthrough here. And there's a lot of work to be done with the materials and the process, and actually changing your design culture as well to work with the available technology. That's what's in it for us as a partnership, and that's what we're trying to push forward all the time. So the goals are pretty straightforward. We're trying to save time on the track, and we're trying to reduce lead time. For me, the most important thing is getting new parts of the track faster than our competition. We're continually inventing performance in the wind tunnel and in vehicle dynamics, and the teams that can deliver that to the racetrack successfully, on time and in full, and get the benefit, will go faster. It's as simple as that. We're effectively in an arms race, a technological arms race with all our competitors. It's also about building our knowledge base. It's really important for us and for Stratasys that we learn. So we have a Stratasys engineer on site every week. He works with our design teams directly, and our design teams also link into their HQ. And we're continually developing the process and the products, and we have beta machines running with their next generation of technology to try and get an advantage ahead of everybody else, but also help them learn about where this technology can go and will go within Formula One. As I kind of alluded to, we're in the business of time. Time on the track is pretty straightforward to see. Formula One is very unique as a sport. We compete with 10 other teams on 5 continents around the world, and about 360 million people see that on a worldwide basis. So it's a pretty big sport. Unlike most other industries though, if you're 0.5% off your competition, you just look rubbish. That's the way it is. So 0.5% will take you from the front of the grid to not even in the final part of qualifying. There's not many other industries where if you're that close, you would look any different than your competitors. So it's absolutely extreme and absolute, and it's done very publicly. So we're always chasing time. You can't do anything about it. The clock's ticking now. I can't go back and have the time I've wasted. But we can buy time sometimes with our suppliers. So in the busy periods, we outsource about 50% of our work because we just haven't got the internal capacity. In the summer, when it gets a bit quieter, we make over 80% in-house. And the bit we don't make is because we're kind of not very good at that technology. Formula One, for us, is the pinnacle of motorsport. What makes it particularly exciting is the GForces involved. So other Formula around the world can go as fast as Formula One cars, but nothing accelerates, corners or brakes like a Formula One car. And these days, with the new regulations and these engines, we're pulling 5G round corners. So in Parabolica in Monza, we're pulling 5G. And when the guys hit the brakes, they're pulling 5G. In a Formula One car, the aero loads are so high, if you just lift off the throttle at full speed, you get over 1G braking, just from the aerodynamic forces. Most supercars would struggle to pull 1G, even hard on the brakes. With a really trick car with very special tyres, you can just about get over 1G. So Formula One is extreme. We also expect a lot of the drivers in the team. When we turn up at a track, we expect to operate the car within 0.5% of the envelope of all the parameters, whether it's accelerating out the corner, holding corner speed, holding the line through the corner, or hitting top speed on the straight. And we expect the drivers to do that, and they generally do. The Formula One drivers are a fairly special breed. We're lucky enough to have ex-world champion Fernando Alonso, who is one of the best drivers in the world. We've now got Stoffel Vandoorne, who's coming up really well. But all the drivers on the grid, if you think about it, it's like playing football for the world. There are 20 guys and girls lucky enough to be able to drive a Formula One car, and that's it. So the competition to get there is fierce, and those who make it are really, really good, even though they don't always look that good when they're on the track. So how do we integrate 3D printing into our business? So this is a very simple view of how we run our business. We employ some very, very clever people at the left-hand side of there, guys who are into the concept of airflow, vehicle dynamics, and really pushing the boundaries of physics and science. By the time you get to the race itself, it's run like a military campaign. So the guys who go around the world, we take 45 people around the world to every race, and those guys effectively run on a season from March through to November, Every day is scheduled for them, all their freight arrives, the hotel and everything. And we have to manage everything in between. And effectively we go from blue sky thinking at the left-hand side of the chart to kind of the hard stop of the race starting at the right. So the car as engineered is where the design office work. The car in production is what manufacturing make, and the car as race is what we make. Although it sounds very trivial, checking that the car we're racing is really what we conceived is a task in itself. It's very easy along that journey, especially when you're running really fast, to lose track of it. And even the CAD models between the aero design and the final machine tool, we don't take it for granted that the CAD model is exactly the same, because things just subtly change. In terms of 3D printing then, this is how we've exploited the technology so far. First and foremost, we saw an opportunity to get parts onto the Wintle Model faster. And that's kind of the space we've been in before. So the Wintle Model is a 60% scale model of the car. It's controlled by the regulations in terms of how long we can run it and how many hours a week we can run it. And also we have to balance that with CFD. So we're continually trading real data off a model versus what we can do in CFD computers. Visualization is also a lot of the stuff you see around the show, gives engineers the opportunity to actually touch and feel something. So again, when you're working in CAD screens, it's very easy to get slightly lost, particularly on the complexity of front wings, and the engineers will occasionally produce something we just can't make. So very easy, do a quick check, get something made, give it to the engineers, let them play with it, touch it, feel it, and see whether they really think we can make that stuff. Human interface components is, again, something we've been on the edges of, but really stepped into. And we've got an example of that later on in the presentation, where we've got a real game changer in terms of being able to give the driver something to touch and feel when he's in the factory before we actually go to production. Mock-up parts. From now through to January, we are designing and building our new racing car. We haven't started building it yet, but effectively, unlike the normal automotive industry, we design and build a brand new car every year. So there's about 16,000 components in a Formula One car, and all those start in August, and by the time we get to the second week in January, we'll be trying to build a car. There's a lot of simultaneous engineering in that, and the mistakes are made. To try and minimize that, we do have a mock-up. So 3D printing is used extensively in the mock-up, allows us to change things, again do all the pipe and wire runs on a real full-size model of the car. Where we've stepped into over the last few years, and what we're doing with Stratasys a lot, is moving into the molds. So we make rapid prototype molds, we take one shot off. It's a lot quicker than programming aluminium mold tools or making patterns and molds, and also actually making full-size components to go straight on the car. Obviously you'll see with the some of the printing technologies you can combine materials. So where we've got rubberized materials, particularly around the suspension seals on the car, where we used to try and make a carbon fibre piece and then bond on rubber to keep the air from coming out between the suspension, now we can just make all that in one piece with various grades of rubber, and we can tune that as the season goes on. So if we find that we're leaking too much air, we make the rubber stiffer. If it's not durable enough, we can make the rubber softer depending on suspension movement. So it's kind of adapting the technology to what we need to get the performance out of the car. Pit equipment is something that changes all the time. You'll see the guys on the TV when they do a pit stop, we dive onto the car to try and keep the brakes cool, but it's more than that. So actually when the car's in the garage, we have to preheat the oil and water. So we're blowing hot air into the car when it's on the garage, and also circulating hot oil and hot water through the car. So there's a great opportunity, save us having to tool up and make solid parts out of aluminium. We can make 3D parts, print them very quickly. As the design evolves, we're not constrained by what we can do in the garage. We can move quickly. And I guess finally, at the track. So we do now take a machine to the track. Initially, it was just to get some simple gurney flaps and things like that, quick and easy things that we might need to do before we go to a particular race. So we modify the car for every race. We get a design change every 10 minutes on the car on a 365 days in a year basis. So it's non-stop. If you're not careful, you can consume a huge amount of time internally designing production engineering and making parts that are only going to run for one race. So little simple parts that are very, very race specific. It's a lot better, cheaper and quicker just to make them at the track when we need them. And if the weather turns out to be different than you expected, you don't even need to make the parts at all. So I'm just going to talk through a couple of examples of things we've done this year, which are kind of game changers for us. So rear wing development in Formula One is quite an art form. The rear wing main plane is reasonably complex. It has a drag reduction system on the flap, which allows the car to go faster on a straight line. But we're always trading stall on the wing with downforce. So the wings do run right on the ragged edge. If we get the wrong type of dirt and debris on the leading edge of the wing, it will stall, and that does give us problems. So when we're developing the car, and we had new regulations this year, it's always a bit of a guessing game as to what the car is really going to do in the real world compared to CFD or in the wind tunnel. Because in CFD the air is nice and clean, in the wind tunnel it's also air conditioned and comes at the right temperature. On the racetrack, somewhere like China, it's very dirty, generally rains, and you get grit and flies all over the leading edge, which destroys the aero surface. So we headed into the season with a suite of wings. Realised we had a potential problem. We needed to get something out really, really quickly. Conventional design, tooling and production of these parts takes between 4 and 5 weeks to go from the concept on the left, which is as released from aero, so it's already spent time in the wind tunnel and CFD. But by the time we get that onto the race car, we'd normally allow, say, 4 to 5 weeks. If it was absolutely critical, and sometimes it is, and we stopped everything, put every designer we could on it, and every production engineer we could, we think we could do it in 10 to 12 days. That's as fast as it goes. There's a lot of tooling, a lot of laminating, and it all has to be proof loaded and proof stressed before it can go out too. With Stratasys, what we were able to do was go straight to FDM mold tools. So we cut out a huge design process, go straight from CAD model, upscale from 60% to full size, and go straight into manufacturing of a mold tool. We then can laminate the skins straight off the mold tools. While that's happening, in parallel, we're machining an aluminium skeleton effectively to hold that structure. So the car's effectively skipped straight through from concept into production, the rear wing design. And we actually got to the race with a brand new shape of rear wing main plane, end plates for carryover, and we did that in just 7 days. So to kind of reiterate, it went from what Aero thought they wanted to run the particular race, we had it on the track in Shanghai 7 days later. Now that was really important for us because what we really needed to do was learn. There was some compromises. That wing did weigh more than the carbon wing we'd normally take, and that gave us quite a struggle. We had to make sure the stresses of the pylon and the mounting were going to hold that extra load because the aluminium substructure under the carbon wings was heavier than we'd normally have in a carbon wing. But the important thing for us was learning the aerodynamics. So what it enabled us to do within 7 days was validate an idea we'd had in the tunnel and something we'd had in CFD, get real data from a real car on a track, and then take that learning forward. So once we'd done that, we then fully productionized it with a few tweaks with what we'd learned, and we went to our conventional method, but it then took us 4 weeks to get a carbon version to the track. In the meantime, we made a second one of these, and that was in our arsenal to go racing while we waited for those 4 weeks to tick by. I mentioned earlier about kind of the touchy feely thing. I think this is something where the printing technology has a great deal to offer. So we need to give our drivers a steering wheel to feel at the start of the season. They're quite fussy about where they sit, what they feel, how the controls all work. Particularly someone like Fernando, he'll have very firm views about what he can do in the car. And these guys are kind of PlayStation kids in reality. So without looking at what they're doing, they are changing settings on the wheel pretty much every lap. They're changing the way the engine harvests energy into the battery, they're changing brake balance, and they're changing the diff settings. It's pretty much all they can do. Apart from that, a lot of the stuff you hear on the radio is when we've got sensors that are failing on the car or systems not working correctly. So the race car runs with about 250 sensors, and it's trying to look after itself as best it can, but when a sensor fails, it is going to affect performance. So a lot of the noise you hear on the radio is actually getting the driver to select menus to turn sensors on or turn sensors off to stop it affecting the car performance. So normally it would take us 2.5 days to make a rapid prototype steering wheel, and to be honest, it was pretty clunky. It had no functionality, none of the switches or dials moved, so it was something a guy could hold. He could kind of get a feel, he could touch where all the buttons were, but he couldn't actually use it. So with Stratasys, we've been able to do that in 6 hours, and because of the technology, the switches work. He can actually feel the tactile grip rather than just be a plain stereo grip. And we can even go and sit it down on the simulator on the mock-up, and he can kind of have a play with how that feels as he interacts with it, trying to get the steering lock on the car. So what that means for us, in the past we'd have the driver in, we'd get his thoughts and feelings on what he wants to do with the steering wheel for the coming season. We'd then go and do a lot of design work, we'd make a part, during his next visit he'd come and try it, give us his views and opinions. If you're lucky, you get 1 or 2 iterations in before you go testing in February. With a new process, we can have the driver in. They're normally in for 2 days when they come and see us, spend time in the simulator. So we'll get them in on at the start of day 1, give them our latest thinking, let them have a play with it, take that away. Before the end of the day, when he finishes his session in the simulator, we've already made the next version. So in a 2-day period, we can get 4 iterations through that he can actually try, give his opinion on, and take that feedback straight into the main design. From that, we then design a carbon frame, furnish it with electronics, and then test the whole system. But a full-size steering wheel costs over £35,000. It's crammed with electronics and switches, so you don't want to be making those and making mistakes. So trackside operations, here's a quick picture in our garage from Singapore. So this is a machine we fly around the world. It's very small, can only do limited parts. Most of the parts that are made in there are actually designed in Woking in the factory. It just takes too long for the few designers that are out at the track to spend time designing bits, but if they have to, they can. So if we have a failure of a simple bracket or something where we need to keep some pipes or wires apart, they will just knock something up at the track and make it. But if it's aero parts, we're generally designing that in Woking, we're taking it straight from the CAD models, exporting the data to the guys at the track, and then they print it off. And they will literally print between sessions. So Friday for us is the big day. We turn up at the track, having run the simulator, done all our modelling in the background. So we've got a pretty good idea how we want the car to perform, but there's nothing like real data, nothing like being there on the ground at that track at that time. So the guys then will decide they want slightly more or slightly less downforce from certain parts of the car, and we'll, in real time, back at the factory, design, check those parts through CFD, issue them overnight, and we'll have that machine running in the morning. Most of the parts are fairly quick to make. Again, they tend to be a bit heavier than the carbon parts would make if we were making them in the factory, but it's the speed and the response and the ability to change in the field that really what we're going for. And the big thing for us, why we kind of talk about time a lot, the race is a real deadline, it's a real hard stop. Whether our car is ready, whether it's fully engineered in time, whether we've actually got all the right bits in it or not, no one really cares apart from us and our fans. It's a huge story if we ever don't get a car out on the grid for whatever reason. So that kind of hard stop deadline every 1 week or every 2 weeks in the season just drives our whole business. Once we start racing, the time just flies by. It literally seems like yesterday we were going to Australia. Here we are, we're now in the back half of the season, starting the final flyaways. So that continual drive, that continual push, and that arms race I talked about earlier is very real for us. We never stop, and once we do stop, everyone thinks we pack up at the end of the season. Actually, that's when it gets really busy, so we're now designing and making the new car. So thanks for spending some time with me this morning. I'm happy to take 1 or 2 questions for a couple of minutes. If I can hear you, have to shout up. If you've got any detailed questions about what we're doing with this technology, please go and see Amos and the guys on the Stratasys stand. We've got a simulator there. I think Fernando's posted a lap time for Monaco. If any of you can beat it, please leave your card with the guys. They're very interested in talking to you. You need to weigh about, well, less than 80 kilos and be fairly short, but apart from that, the time is important. And we've got a model show car out to have a look at as well, which is a full-size replica of last year's car. Okay, thanks very much everybody. Hope you have a good show. Cheers.